Today I'm going to cover the interference of light. We'll start with interference and we'll go on to diffraction, which is an especially important topic. So we've done interference in very general terms for waves from the superposition principle. But now let's see what happens with light in particular. Okay. Let's say that we've got a double slit. So we have something that blocks the light, opaque, with two narrow slits separated by a distance d here. So d will be the distance between the slits. The slits should be narrower than the distance between them. Furthermore, we're going to have a screen over here. So we've got light waves coming in from the left to the right. They go through the pair of slits. Now, what I'm going to trace here is not the wave fronts. We'll do that in the next section with diffraction. We're going to trace the rays, the direction that the light moves. So the red doesn't show up very well on this, unfortunately, but I think you can make out at least the lines. I've made sure to put the labels, the variables, in white. So here's ray number 1 from the first slit going up here, and here's ray number 2. Now what happens when they meet at the same point on the screen? I'll label that y. So y is increasing upwards, and I'm going to mark y equals 0 being across from the middle of the two slits. Now, the angles that the rays make with respect to this horizontal line are theta 1 and theta 2. Let's see here. So keep in mind that you've got the wave fronts, you've got the ripple pattern here. Now, if the two rays are in phase when they meet, then you're going to have constructive interference and a bright spot on the screen. But if they are out of, so their crests meet and their troughs meet. But if they are out of phase, the crest of one overlaps the trough of another, you get perfect destructive interference and you'll have a dark spot on the screen. Now in practice, we're going to wind up with a series of bright fringes where you have constructive interference where they overlap with their, I'll get to that, sorry. Now let's say that the distance from the double slit here to the screen is a distance L, capital L for length. Furthermore, I'm going to make the assumption that the distance from the slits to the screen, L, is much larger than the distance between the slits, D. That allows me to make a small angle approximation here. So, in that case then, because they're moving out to such a distant screen, and the distance between these two is so small, theta 1 is about the same as theta 2. And I'll just label both of them with theta, a single one. Now, in that case, let me redraw this little section right here around where the slits are. So here's the card or whatever that has the slits cut in them. First slit, the second slit. Here are the two rays going out here, R1, R2. Now, R is standing for the distance, the path that this first ray travels out to the screen. And R2 is the path that the second ray travels out to the screen. Now, because the screen is so far away and the slits are so close, remember, those angles are about the same, which means also that these two rays here are parallel. That simplifies the geometry nicely. Because they are parallel, then whether they arrive in phase or out of phase depends on delta R, the difference in the path length from the first to the second. The second one, as you see the way I've drawn it here, is going to travel that much farther before they get out to the screen. Those sections would be the same length, and that's the difference there. So what is delta R? That's the path difference. If I have a plane wave coming in to hit the slits, then there's a wave front parallel to this material here, and that means that the wave emitted from the first slit is in phase with the wave emitted from the second slit. So let's take a look then at the map. Okay, we've got here make sure that gets all in there. Yeah. All right, recall that the phase difference, delta phi, is equal to, we had this in previous chapter, 2 pi delta r over lambda. Delta r is the path difference, lambda is the wavelength, plus delta phi naught. And that phi naught, remember, is your initial phase, or the inherent phase. Now, in this case, because I've got a plane wave coming in with parallel rays here, if there's a crest emitted from this one, at the same time there will be a crest emitted from that one. So the inherent phase difference is 0. That simplifies the math now. By the way, you could have it arrive out of phase and it would change the results, but the physics would work out the same way. Now, delta phi, if I want to find the places for constructive interference, then I know that the phase has to be, the phase difference must be an even multiple, the phase difference must be a multiple of 2 pi, an integer multiple of 2 pi, either 0, like that, or 2 pi, 4 pi, 6 pi, so on like this. So remember that m, that index number m, counts the number of multiples. It's an integer, 0, 1, 2, and so on like that. So I put in for constructive interference, m times 2 pi equals 2 pi delta r over lambda. Cancel out the 2 pi's, and I solve for delta r, and so I get delta r equals m lambda, where m is 0 or positive integer. I turn the camera a little bit. Okay, so again, this is for constructive interference and therefore bright fringes. Now, delta r, that path difference here, if I look at just this right triangle, all right, here the two rays will be coming out. The distance along the hypotenuse of this triangle is d, this distance between the slits. If the rays are emitted at an angle theta away from the horizontal, then the angle that this side makes, the adjacent side, will be theta with respect to the vertical. So that's an interior angle of the triangle. And then this side here, the side opposite theta, is delta r. So sine equals opposite over hypotenuse from the SOHCAHTOA rule, if you remember. So sine of theta equals opposite over hypotenuse, that's delta r over d. Solve for delta r, which is what I'm interested in, the path difference. That's d sine theta. Okay, now, make sure that got all the way on there. Yes. So now, if the path difference is going to be an integer multiple of the wavelength, then path difference is d sine theta. Is an integer multiple of the path length. Now, if I look only at small angles away from straight on, so theta is a small angle, I can use the small angle approximation, where the sine of theta is about equal to theta, again in radians. So, d times theta, and that looks like a derivative there, not, or differential, it's not, it's just d times theta is about equal to m lambda. Solve for theta, it's equal to m times lambda over d. So, now that subscript m, and I haven't relabeled m because I've written it up here and I've run out of room. But remember, it's 0 or a positive integer. And to tell you the truth, you could even put in negative integers, but it's symmetrical, so we'll just use the positive integers for either side of the center. So this gives you the angles to the bright fringes, the areas of constructive interference. M times lambda over d. Now, this means that if the wavelength is longer, the angles to the different fringes, the bright fringes, will be wider, and therefore the bright fringes will be spaced farther apart. If the distance between the slits is larger, though, that'll bring those bright fringes closer together. Now, what about the actual position on the screen of the bright fringes? We have a little more space here. Now here again are the two slits, and then you have the light rays coming out, and then you have the screen over here. Now in this case, here's a ray coming out, a pair of rays really, to a point Y on the screen. And then I draw in, I should draw this in white since it's not a light ray. There we go. The distance from the slits to the screen is L. So again, I have a right triangle, Y for the opposite length, L for the adjacent length, and I don't care about the hypotenuse. So the tangent of theta is opposite over adjacent, that's Y over L. Now, if again we're looking at small angles away from the horizontal, then the small angle approximation lets me say that tangent of theta is about equal to theta. Basically, for small angle approximations, the sine of theta is about equal to theta, tangent of theta is about equal to theta, and the cosine of theta is about equal to 1. Those are three very useful small angle approximations. All right, so that means that theta is about equal to Y over L. And I want to solve for the position of that bright fringe on the screen, so solve for Y, that's theta times L. And then I sub in theta. So theta is m lambda over d, and therefore the screen positions on the y-axis for the bright fringes are y subscript m equals m lambda L over d. And again, for m is 0, 1, 2, 3, so on, integers. Okay, so that tells you where on the screen, if you know what your distance to the slits is, the wavelength of light, and the distance between the slits. Now, I'll show you the pattern on the next board over here where I've drawn it out. Okay, now let's take a look at the intensity of the light. We know where the bright fringes are, but how bright are those fringes? Now, recall that the intensity of light, which is also the flux, the brightness, is proportional to the amplitude of the wave squared. Now, capital A here, since we've got multiple waves interfering, then capital A I'll use for the total amplitude, whereas I'll use a lowercase a for the amplitude of the individual light waves that are emitted from the slits. Okay, so if I is proportional to A squared, then, to write it as an equation rather than a proportionality, I is equal to some constant times A squared. So, what is A then? We'll come back to this here. What is A? Recall that, this is equation 21.36, recall that the amplitude for waves that are interfering is absolute value of 2 lowercase a, the amplitude of each individual wave, times the cosine of delta phi over 2. Now, delta phi, remember, is the phase difference between those two waves. So what is delta phi in terms of the geometry? Well, delta phi, you also recall, is 2 pi delta r over lambda plus the inherent phase difference delta phi naught, which, as I've said before, is 0 in this case. Now, delta r is the path difference, the difference in the distances the two light rays travel, and lambda is the wavelength. So I've got that. Once I've set that 0, the path difference is delta r, and I've redrawn my diagram here. So you've got the distance between the slits is lowercase d. The angle that they're emitted horizontally, the angle away from horizontal is theta, which also winds up being the interior angle of this triangle here. And the difference between those distances is delta r, which is the opposite side of the right triangle. D is the hypotenuse, delta r is the opposite side. So the sine of theta is opposite over hypotenuse, delta r over d. So delta r is d sine theta. Of course, I did all of that before. So I put that in for delta r here. Now, 2 pi, so the phase difference is 2 pi d sine theta over lambda. So, let's use the small angle approximation. Sine theta is about equal to the tangent of theta. Well, why would I want to put it in as the tangent? Why not just go straight for theta? Because the tangent being opposite over adjacent, opposite over adjacent sides, is useful in that I've got, that is y over L. So, I can put it in terms of other things like the distance to the screen and the position on the screen. So that's useful to me. So I sub that in, y over L for sine of theta. So now the phase difference is 2 pi d times y over lambda L. And I substitute that in for the phase difference here. That gets a little crowded at the bottom of the board. So the amplitude, the total amplitude, is the absolute value of 2 lowercase a cosine of 1/2 times 2 pi, the 1/2 and the 2 cancel, d times y over lambda L, and simplifying, that gives me amplitude is 2a cosine pi d over lambda L and times y inside that cosine. Now, what I want, though, is the intensity. So I substitute that in there. Okay, the intensity is some constant, whatever it is, times the amplitude squared. Well, I put in for amplitude squared, I've got to square that 2a cosine blah, blah, blah. I can get rid of the absolute value symbols because when you square this, it's a real function, it's not imaginary, you can only get a positive number. So 4 times ca squared cosine squared of pi d y over lambda L. I can do one more thing that's kind of useful. That's ca squared. Remember, if we didn't have the multiple slits, if we just had one slit, well, we'd only have one light ray, and the intensity of a single slit would have been the same constant times lowercase a squared. Proportional times a squared. So what do I write I sub 1 for the intensity given by a single slit? And I put that in, that's ca squared, that's right here. So I get 4 times the intensity from a single slit times the cosine of that function there. Which means, if I want to look at the intensity of the bright fringes, that's where you get the maximum intensity. Here are the fringes, here's the screen. Now I'm making the intensity, y is increasing upwards, the intensity is increasing to the left. It's an awkward way of drawing it, but I'm trying to plot several things at once here. And I want it to look more or less like the arrangement you'd actually have. So the intensity, so here's a bright fringe in the middle where m equals 0. That's the first fringe, is labeled by m. M equals 1 gives you 2, one here, one here. M equals 2 gives you these two, m equals 3, and so on. You want to find the intensity. The intensity of the bright fringes is the maximum intensity. So where is the cosine squared at a maximum? Well, wherever you've got these fringes. But the maximum value of cosine is 1. Put that in, that means that all of this part is equal to 1, and the maximum intensity is 4 times the intensity of a single slit, provided by a single slit, in the absence of interference. Why isn't it 2 times the intensity of a single slit? After all, you've got 2 slits. Why is it 4 times? Because you've got to conserve the energy. Light is a form of energy. So if you have areas where there is 0 intensity here, you have to have other areas where the intensity is greater than, it has to make up for that missing flux, that missing intensity here, that missing energy there. It's just moving the energy around, distributing it in different places in space, rather than getting rid of it entirely, which you can't do. So it simply means that because you get regions of lower than average intensity, you have to have regions of higher than average intensity as well. Okay, that gets us through interference. Now, interference is when you have multiple sources, whether they're in phase or out of phase, doesn't matter, but multiple sources, and they are, well, the sources are interfering with each other to provide this. What if we only have a single slit? Do we just get an even, broad illumination of light? It turns out that you get something that is a bit like interference, but called diffraction, when you don't have separate sources, but a single source. So we'll look at diffraction next. But one more thing I should say about the interference pattern from a double slit is that this was studied in great detail by Thomas Young in the early 1800s. He lived in the late 17 to early 1800s. Thomas Young was called by one of my freshman college physics professor, Jack Taylor, was referred to as the last man to know everything, meaning he made great contributions to a wide variety of fields. He was a medical doctor. He did work in the materials properties. He did work in optics and so on like this. He worked on, maybe also on blood flow. And so you'll see his name in things like the Young's elastic modulus, for how springs work, how things are compressible or stretchable, and in Young's double slit experiment, as well as maybe some things outside of my own area, like in biology. So, now what about diffraction? Let's first work on the diffraction from a single slit. Turns out that diffraction is more complicated in practice than interference is, and we're not going to do it in the full mathematical way. A lot of what I'll describe is really qualitative. You can thank me later. The first thing that I should show you is what's called Huygens principle. Named for the Dutch astronomer Christian Huygens, who, among other things, he worked on diffraction patterns of light. He worked in astronomy. He worked on how pendulums work, and he really helped create the first really accurate pendulum clocks, like a grandfather clock. Okay, now in this case, what we're interested in is his treatment of the wave nature of light. He was a little bit older, but contemporary with Sir Isaac Newton in England. And while Newton was, in his book on optics, promoting the idea that light travels as particles in straight lines till it hits something, Christian Huygens had the idea that light travels as a wave. And I think really the debate goes back far more ancient than either of them, but they were the two prominent scientists promoting the two contrary ideas at the time. By the way, I will say that while we do treat the wave nature of light here, Newton's particle nature is also true. There's the photon of light, which is a particle of light. But the photon has both a particle and a wave nature, and these were really not reconciled until Einstein in the year 1905. So the beginning of the modern era of quantum mechanics. Okay, so Huygens principle. There are two things to do. First, before you get to the two things to do, treat light traveling as a wave. So, the first step, if you have a light wave somewhere, take a look at the wave front, where the crests are, the line of all the crests in the wave. Take each point on the wave front as the source of a spherical wave, actually you call it a spherical wavelet, meaning a little piece of wave, that spreads out at the wave speed in all directions in a spherical shape. So you've got each, I'm not going to try to write them, I'll just say, each point on a wave front is the source of a spherical wavelet that then spreads out at wave speed. Number two, the shape of the wavefront at the next moment in time is simply the curve, the line, in a very general sense, the curve that is tangent to all of these wavelets. So, as an example, let's say that I've got a wavefront here. This is you're looking from the top onto like a ripple tank, water waves or whatever, looking down onto the surface. all right? And we know that it travels like that. Say it's a plane wave there. Now, let's just take this one. I'm going to take every point on that wavefront. Well, I can't look at every point. There's an infinite number of points on that wavefront. I'll take a few of them. And I'm going to draw a spherical, well, circular, because it's on a flat chalkboard, a circular wavelet of the same radius for each point. Now, let's say that I draw, whatever distance away. So I'll use my thumb and forefinger as a compass. This is a nice trick, by the way. Now, notice I haven't drawn complete circles for all of those. All I really care about is where they just about intersect with each other. So, at the next moment in time then, the next wavefront is the line that's tangent to all of those little wavelets. Now, after that, now you've got the new wavefront, which, by the way, if I drew enough of the points, it would have come out to be a perfect straight line, therefore a plane wave again. The fact that I only drew a finite number of points means that I got little bumps in it, but that's just the imperfections of using a finite number rather than the true infinite number of these. As the limit goes to an infinite number of points, the shape goes to a straight line. Now, for the next moment in time, I take points on this here. And now I've got a new wavefront here, and so on. And so you can see that it travels outward, and if you measure how far it travels in each moment of time, you see it spreads out at the same wave speed you had before. Okay. What about a point source, a little point that's vibrating? So let's say that we've got a wave that starts from a single point, not from a plane wave, but it is a spherically spreading out from this point here. So at one moment in time, here's the wave crest. It's just a spot. So I draw with a compass. Boy, I think I should really just, there. I've got a circle. Well, if from one point, a spherically spreading wavelet is a spherical wave from there. That's the only point there. So that's my new wavefront from this point in time. Now, let's draw it at the next moment in time. This is going to be a little trickier. Now, using this for a compass, I can't get all the way around there, but hopefully you will believe me that that makes, I can fairly complete that. And then the next moment in time, you go around and around and around like that, and you come up with another, where all those spherical wavelets overlap, you get another spherical wavefront, and so on. And so that is spreading out as a spherical wave. So this works really nicely. Now, what about, what if I have a plane wave? So, plane wave, you've got the crests all form straight lines as they go forward. What if that plane wave hits a single slit? Well, I'm going to refer to an aperture, meaning an opening in some obstruction. We've got a narrow aperture. What's the difference between going through a narrow aperture and a wide aperture? Let's see, I've got room here. Okay, so I've got a plane wave coming from here, and then, the next moment in time, I know how a plane wave propagates. Now it hits this narrow opening, aperture here. So, I'm going to take a few points here. Now, the thing to notice is, in the middle, where you've got a lot of points that were, you've got points on either side of this area in the middle. This smooths out to a straight line. But look at the edges. See, there are no other points above this one where the wave is spread from in order to make wave fronts that overlap. So your new wave front curves like that, and down at this point, it does the same. It's sort of straight and flat in the middle, but on the edges, what we call edge effects, it rounds out. Now let's look at the next moment in time. Things change. Now I've got to look at each point on this new wavefront. So here I've got to be at the corner. Okay. It's a little more rounded. You've got a narrower area that's perfectly straight, and you're starting to get bigger rounded edges there. If I do it again, it's only barely flat in the middle now. Mostly it's rounded. And anyway, as you go on out in time then, you're going to find as you get farther away, let's say at distances that are much larger than the width of the opening, basically you've got a, for all practical purposes, this becomes a spherical wave at large distances away from the opening. What about if we got a wide aperture? Okay. And again, let's say we've got a plane wave coming in. So, do the same thing again. All right. The edge effects mean that the edges of the new wave front are rounded, but in the middle, where you've got spherical wavelets on either side still, you've got it essentially straight, a plane wave there. Now, the next moment in time, okay. The edge effects start to round out even more. Now I'm going to draw this freehand here and let you trust me on it. But what if I've gone out now, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, I know it's a little bit freehanded, but you see here, if the aperture is wider, it takes a greater distance for the wave to propagate through before it becomes a spherical wave in practice. Basically, the plane wave nature of it stays pretty true a greater distance if the aperture is wider. Remember, you've got to go a distance that is much larger than the width of the aperture before you start seeing the spherical wave shape when it opens up. And that's just a nice geometric treatment. Now, Christian Huygens, Huygens, by the way, the Huygens, it's a Dutch name. It looks a little funny that way. It's actually probably pronounced more like Christian Huygens, and the Dutch have this kind of voiced guttural G. I've never known any other language that does it quite that way. It's tough to pronounce. Anyway, Huygens, slightly anglicized, did not have a full theory of wave propagation, but this principle, this geometric principle, works very nicely in order to show how diffraction works. So, how does this lead to diffraction? Let's see here. What's going to happen is that while I've really just been drawing the new wave fronts, remember that you've got all of these little spherical wavelets. Now, if I think of each point in a way as being a new wave source, of course they're in phase if they're on the same crest. You see these crests and troughs of the different wavelets interfere with each other. And that brings us back to the basic idea that we had with interference a few minutes ago. Except now the wave is interfering with itself, not with a separate source or something that came through a separate opening. Basically, it's all the same mathematical principle, whether you have crests and troughs lining up, constructive interference, or I should have said crests lining up with crests and trough lining up with trough to get constructive interference like that, so it builds up higher, or a crest lining up with troughs to give you destructive interference, or something in between. Okay, so let's take a look at a little basic mathematics for single slit diffraction. Now the book works this out in a bit of detail, but it might be tough to follow. And I'm going to explain a few things the book doesn't. Okay. Now we're still on the idea of single slit diffraction. Okay, so the constructive and destructive interference of the wavelets produces a diffraction pattern on the screen when it goes through an aperture, an opening. So let's have the aperture be a slit of width lowercase a, where the aperture is much smaller than the distance to the screen. So, now I'm looking at a magnified view of the aperture, so the screen would be very, very far away over here. All right. If I take a look, I don't want to try redrawing all of those wavelet crests and things. I'm going to draw the rays, the direction that these things are moving. So let's take, maybe I take a few points along this and look at the direction that the wavelets travel. So I'm looking at light rays. A ray is the direction that a wave travels. Now, if I look at angle theta equals 0, so exactly horizontal, okay, there's the wavelet motion. If they're traveling parallel to each other, well, of course, parallel to each other, but if they're traveling exactly horizontally, there is no phase difference between them when they hit the screen. Therefore, they arrive in phase, therefore you get constructive interference at a position theta equals 0. Okay, so you get a bright fringe at the very center of the screen, at the center of the diffraction pattern. Now let's take a look at what happens when we get, when we're going to look for destructive interference. Now, because of the arrangement of these boards, I'm not going to have much room. I'm going to erase this because I want to look at two examples of destructive interference. Okay, now I'm going to draw those same 5 wavelet points, sources that I had before. Let's see, one in the middle there. Okay. Now I know that going horizontally, theta equals 0, you get constructive interference. So destructive interference has to be some angles away from horizontal. So let's have them tilt up at an angle theta. Okay. Now, here's the neat part about this. If I want destructive interference, then I need to have, the crest of one has to overlap the trough of another. So I'm going to pair these up, because there's an infinite number of these, but I'll look at a finite number. Okay. So, if I were to look at any two of these, let's take two that are separated by half the width of the aperture. So if the width of the aperture is A, half the width is A over 2. Make sure that appears on the screen. Yes. So I'm going to look at this ray and that ray. Now, what's the path difference between them? Draw my right triangle for the path difference delta R. That, if this angle is theta, then that angle is also theta, and that distance is A over 2. Okay? So, sine of theta is opposite over hypotenuse, which means I'm going to get delta R, sine of theta is delta R over A over 2. And that's going to get me, let's see. So delta R will be equal to A over 2 times the sine of theta. All right, that's from the geometry there. That gives me the path difference. But at the same time, if I'm looking for destructive interference, I've got another expression for delta R, which means delta R must be half of a wavelength, or multiples of, odd multiples of half wavelengths. Obviously, if I have even multiples of half wavelengths, I've got whole wavelengths, which are constructive interference. So, odd multiples of half wavelengths. Let's just take the first, the closest one to the main axis, which would be that the phase difference is exactly lambda over 2, half a wavelength. Okay. So I've got these two things. This, for destructive interference, this is not true in general, just for destructive interference, for the first case of destructive interference. And that is true for the path difference to it. So let's equate these two things. So this gets me, if those two things are equal, then A over 2 sine theta equals lambda over 2, and therefore A sine theta equals lambda, I just canceled out the 2. Therefore, what angle do I look at to see these? Well, sine theta equals lambda over A. And if I'm looking at small angles away from the axis, then the small angle approximation says that sine theta is about equal to theta. So theta is lambda over A. Now, notice I don't have an M in there. I'm not looking at every instance of a dark fringe, which is destructive interference, only for the first one. Okay, so this is not a formal conclusion. This is just for one special case there. Now notice, all I've done so far is to pair up this wavelet with that wavelet as they travel out. And notice that for them to be 180 degrees out of phase, or pi radians out of phase, that's what the angle has to be. But that's only for two of those light rays. What about all the others? Because I chose rays separated by a distance of A over 2, then I can take the next pair here, and the next pair here, here, and here, and then by sliding those pairs by looking at matching up pairs along like that, by the time I get down to the last remaining ones, I've paired up every single pair of light rays. I've accounted for every one of them because I had it be half. I looked at ones that were exactly halfway apart. Okay, so that gives me the first dark fringe. What about the second dark fringe? Turns out, if you look at rays spaced A over 4, a quarter of the aperture apart, okay, 1, 2, 3, 4, 5, all right? A quarter of the way apart, let's see here. Yeah, 1, 2, 3, 4 distances, all right. Those two. Now we do the same thing, all right? There's some angle where those are going to interfere. Those will destructively interfere. The path difference is delta R. That angle is theta. This side here is, let's see, there's a right angle. Delta R is the opposite side. A over 4 is the hypotenuse. So now I've got delta R will wind up being A over 4 sine of theta by the same reasoning as before. If I look at the smallest angle that will give me perfect cancellation, then I'm going to have that delta R will again be lambda over 2. Equate those two things. So I'm going to wind up with A over 4 sine theta equals lambda over 2. I will spare you the intermediate steps because they're identical to what I just did, and I come up with the grand conclusion that, after math is done, that theta equals 2 lambda over A. I'm not making a rectangular box because even this is not the final conclusion. Okay, and you can go on, and you can take the, you can slide down which one rays you're looking at, here, 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 here. Now I've taken care of all the ones in the top half of the aperture. Skip down here, 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 here. Now I've taken care of all the ones in the bottom half of the aperture. And then I've taken care of all of them. I can do the same thing for 1/6 of the aperture width, A over 6 spaced apart, and do the same kinds of conditions. So I'll have an A over 6, and I'm going to wind up with theta equals 3 lambda over A, and then A over 8, and I'm going to wind up with theta equals 4 lambda over A over 10, A over 12, and so on. If I take all of the even numbered denominators for the spacings that I look at pairing these up, then I can do the same stuff. If I set it to the cancellation, I'm going to wind up with this kind of general rule here. Then, well, wait a second then. What if I choose only even numbered denominators? Even numbered denominators for these fractions, for these spacings when I'm pairing them up. Why can't I do A for the spacing? That's A over 1. Well, look, if I take these two light rays that are spaced the whole aperture apart, fine, I can get them to cancel out. And then I move to the next. If they're spaced by the whole aperture, there are only 2 rays that won't pair up at all. I can't get any other 2 to be spaced that far apart. Okay, fine, that's just A. What about 1/3 of A? Can't I get 1/3? Turns out if I get 1/3 away, if I space up blah, 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 and I pair all of them up, that only accounts for 2/3 of the aperture. There will be 1/3 of the light rays that I cannot pair up then, because all the others have already been used. What about 1/5 of the aperture, A over 5? You work out you skip over to the next little section, and the next fifth, and you wind up with 4/5 that you can get paired up without reusing any. A light ray can only cancel with one other after all. And you've got a 1/5 left over. If you do 1/7, you'll wind up with 1/7 of the light rays unpaired, and so on. So it turns out that only the even numbered fractions, the even denominator fractions, will work and allow you to cancel out all of the light rays. Okay, And that's something the book doesn't explain, so pay attention to that there. All right, so what we found then is a pattern. For spacing of A over 2, light rays spaced A over 2 apart, we get theta is lambda over A. For A over 4, we get 2 lambda over A. A over 8, 3 lambda over A, 4 lambda over A, and so on. So the dark fringes, this is for perfect destructive interference, the dark fringes are spaced out I think dark fringes ought to be a good name for a golf band. Anyway, the angles to dark fringes, that's on the screen, are theta sub p. I've already been using m. I'm going to use p, which is a different set of numbers. Theta sub p equals p times lambda over a, where p is equal to 1, 2, 3, 4, and so on. I know that I cannot have p equals 0. Again, p is just an index number. I can't have p equals 0 because I've already shown that the straightforward position would give me, does give me perfect constructive interference, not destructive interference. And so the pattern then, for single slit diffraction, there's my slit in the material, and here's the screen. Then the pattern where the intensity will be drawn increasing to the left here. Okay, that's straightforward. I get one big, bright central maximum that's twice as wide as all of the other maximum. And then down to the first dark fringe, second dark fringe, third, and so on. Okay, so this is going to be P equals 1, 2, 3, and so on. And down here you get symmetrically the same. Got to give a little more room. This is also the P equals 1 first dark, the first minimum, the first dark fringe. On the bottom side, P equals 2, 3. Now notice here that the central maximum is twice as wide as all of the other maximum. And that's because there is no dark fringe in the center. It looks as if it's skipping a lot. Now the angles to these, by the way, are the angles from straightforward to whatever point you're looking at. So that's theta. Now, what are the positions on the screen? If I take y to be the position on the screen, then, well, all you're doing is taking the tangent of that angle being the distance to the screen, the screen position divided by the distance to the screen. The geometry is the same as for interference a minute ago. And that's going to get you, let's see, tangent of theta is equal to y over L. And that's going to mean that for small angles, theta is about equal to y over L. And I've already got theta sub p equals p lambda over a, so p lambda over a equals y over L, solve for y, and you wind up with y, I'll subscript it with a p, is equal to p lambda L over a, with p equal to 1, 2, 3, 4, and so on. Okay, this again is the position of the dark fringes, not the bright ones, which take a little extra trick on the math. And one last thing then about this is that the width of this the width of the bright central maximum, as I said, it is twice as wide and considerably brighter than the other maxima. All the other maxima are the same width as each other. This width, which the book uses W, lowercase w for, which conveniently stands for width, is equal to 2 times the spacings of any of the other dark fringes. So if you go from, p equals 1 to p equals 2, you've got a spacing of lambda L over A. So 2 lambda L over A, width of the central maximum. What is that, and what's important about that? Now, the diffraction pattern is dominated by this. This is what you see the most, because it's so much brighter and white. And you may or may not even notice these fainter bright fringes out there. So, this width here, notice that the width is proportional to the wavelength of light you use. So let's say, for example, blue light has a short wavelength, red light has a long wavelength. That means that the width of a diffraction pattern will be much wider for red light than it will be for blue light with the same aperture. For that matter, the fact that it's proportional to the distance to the screen is not surprising because it's spreading out as it goes, so you make the screen farther away, the pattern gets bigger. Not physically interesting, at least not to me, but also look at the aperture size. This tells you that if you make the aperture wider, the width of the central maximum gets narrower. It's inversely proportional to the width of the aperture. So, a wide aperture, you don't get much of a diffraction pattern. If you have a narrow aperture, the light spreads out. In fact, in a sense, the wave-like nature of light becomes more evident when you use much narrower slits. If you use a broad slit, just a big opening, you don't really notice the wave-like nature of light, which is what it takes to produce this. You get more of the old classical style, this is still classical physics, but the ray-like nature, where you get sharp-edged shadows and such. Okay, and we'll get into a bit more on that when I bring you to circular aperture diffraction, which is, actually, the book doesn't cover it in much detail, but boy, it can be very important in ways. Okay. Now let's see, I have skipped over the diffraction grading section in the book, only because there's more math, but the physics is really not much different. But I want to illustrate it for you. A diffraction grating is it's where you have a large number of slits parallel to each other. So think about a 2-slit, all right, I've got 3 fingers up there, like the Boy Scout salute. If I've got 2 slits here and here, I get that interference pattern in particular spots on the screen. But what if I have 1,000 slits? You get something that looks like this. This is a piece of cardboard, that's got a diffraction pattern, a diffraction grating cut into it. Now, you can see right through it, but if you notice, there are bands of color that show through because of the fluorescent lights in the room. In fact, if we look up at one of those, there we go. Trying not to just take pictures of my nose here. Now, you can make out the individual colors that are in the fluorescent light. And it creates a diffraction pattern, really an interference pattern from thousands and thousands of different spots. This one has 1,000 slits cut in it for every millimeter across. So this is a very fine one, and it spreads the light out very broadly. In the case of the diffraction grating, then you don't wind up with exactly the same pattern as the 2-slit. Let's see, that's a 1-slit there. You don't get exactly the 2-slit diffraction pattern, interference pattern. You wind up with broader spacings between the lines. So a few uses of this. For one thing, let's take a laser. Okay, now I'm going to turn this around to look at the wall over here, which will be my white screen. Now turn off the lights. Now if I shine a laser through this, okay, there's a laser with a green spot on the wall there. If I shine it through this card, now let's see, you get lines that are spaced out very broadly. I'm going to step up closer to the board here, the wall. Let's see if I can capture more of these lines, bright spots, constructive interference spots. There we go. Now, notice that I've got a bright central maximum for this interference pattern. Remember, compare this to the two-slit interference rather than to the single-slit diffraction. It's called a diffraction grating, but think of it in terms of interference, because you do get multiple sources as you go through. All right, so there's the central one, which looks the same whether I've got the card not in place or in place. And then you have your first maximum on either side of it. Now, why am I getting separate points there? Not sure. I may have some imperfections on this that are causing it to give me multiple spots on those. Or it may be the diffraction from the single aperture combined with the interference from the interference pattern. Okay, now look what happens when I go to a longer wavelength, like red. Let's see if red gets on there completely or not. Okay, if I've got the red light there, now look how much narrower the green is. Red is a longer wavelength, green is a narrower wavelength, a shorter wavelength. Another thing is that the diffraction grating can be used the same way a prism is in lots of ways. Okay. Now, I'll have to lower the camera. All right. Here I've got hydrogen gas in a discharge tube. It's emitting a range of colors, which can only be seen when you take the diffraction grating here. Now, it looks like those are going to be a little bit dark in this. Let's see if I can carry this a bit forward. There we go. There's violet, more blue light, and there's some red. If I could rotate this properly. Okay, the blue, the red. There's also a purple one, but the room is too bright to make that out. I've already turned off the lights even still. You should get the same thing on the other side. The floor is too bright over here. All right, so you can see those colors, at least a little bit. Now, I'm going to put in a tube that has air in it. These things are a little warm. Yeah, hot to the touch. That's got about 5,000 volts going through it. It's okay as long as I don't touch inside those there. It's got a very helpful sticker. Danger, high voltage, do not stick your finger into the socket. It's about as useful as do not stick your tongue into the outlet there. And you would think, I mean, here we are, PhD physicists, and they have to tell us not to stick our fingers into the 5,000 volt sockets. That's a bit brighter. Now let's see what colors we see. Now there's a there we go. You can make out a lot more colors are emitted. Each one of those vertical lines, roughly vertical, with a different color, it is an image of that tube, but an image at a different wavelength. So the different wavelengths of light are spread out at different angles. And this allows us to separate the light into its component colors and to look at the chemical spectrum. So this shows, you can identify the molecules in there. You can see a bit of it over the dark of my thumb. Anyway, this is useful for spectroscopy then. Now, one other thing, to illustrate diffraction, it's interesting that you do not even need a slit to, you don't need a slit to make a diffraction pattern. You will get a diffraction pattern with only a single edge. So here is a knife blade, right, just a pocket knife. Now, shining the laser light on the wall, if I move the knife to cut that laser beam off, if I do it just right, there, you can just make that out, you get a streak. I'm trying to make it horizontal. You see that horizontal streak? That is the diffraction pattern of the light as it diffracts around the edge of the knife blade. Now, earlier when I was setting this up, or honestly playing with it, I was able to get a ripple pattern with that, but I haven't been able to reproduce that since. Now, with the red laser light, the human eye is so much less sensitive to red that this does not show up as well. There's the streak there. And this camera doesn't seem to be as sensitive to red either. Okay. So that gets us through interference and diffraction. Diffraction through a single slit. Let's take a look at diffraction through a circular aperture. Okay, now I've gotten, boy, I've written 4 pages on this myself, 3.5. But it's really qualitative more than quantitative. All right, if you have a light wave coming through a shape other than a slit, you can numerically, not necessarily mathematically, some of them can be tough, but I think probably all of them can be solved analytically nowadays. For any other shape aperture, let's say that I've got there. That's a piece of cardboard with a circular opening in it. Light wave is coming through it like this. So how does the diffraction pattern ripple outwards? Well, it turns out that for every edge to your aperture, you wind up with a streak, a diffraction pattern like I showed on the knife edge, a streak that is perpendicular to that edge when you get to the screen. So this edge here, which is vertical, will produce a horizontal streak. So let's say that we've got a screen over here. The light's coming through it like that. This edge there, let's say that I had, if light were not a wave, if it were only a particle, no wave nature at all, then you'd get a shadow, a bright circle in there, and then dark shadow all around it. But the diffraction says that, I'll use blue for this here, hopefully that'll be picked up there, says that for every edge to this, you get a streak perpendicular to the edge. And then over here, this is a streak perpendicular, and those two will interfere with each other to make bright and then dark and bright and dark as it goes on out, an interference pattern. Actually, it's more like single slit diffraction still. But now, look at these two pairs here, here and here. So there's a bright streak and there's a bright streak, and they combine, and you've got dark bands there, and here, and so on. There's an infinite number of points on those edges that can be paired up in, and what you wind up with on the screen is a bright central maximum that is circular, and then you have fainter bright fringes with dark fringes in between surrounding it. This pattern here, let me see if I can draw it a bit better. That's in that blue, and the colored ones don't show up nearly as well as the white. The pattern for a circular aperture then is like a bullseye. You get a central bright maximum, which is twice the width of all the other bright fringes. Like that. And then the ripples go on out. This is called the Airy disk, named after the British mathematician George Airy, who was the first one to describe it mathematically. Now, it looks like the position of the bright central maximum, the dark fringes, the bright fringes, and so on, along any axis through the center, should be the same as for single slit diffraction, because you're pairing those up. But it's not exactly. It's similar, but not exactly the same. And that's because you've got these coming in at different angles that also add to the interference. That's why this became so much tougher to do, because you've got two dimensions you're working with, not just one. Nevertheless, so if you look at the Airy function that describes this, which you would get to in more advanced mathematics. So, what's important to know about this is the angular radius, and therefore the angular diameter, 2 times the radius. Now that's the angular size means if we take from a point at the very center of the aperture, draw a line to the center of the diffraction pattern, that's our reference line. Now if we want to look at the edge of the bright maximum there. Now what's the angle between those two lines? That's the angular radius of the bright central maximum. And the angular distance to any of these other points is measured from that same central reference line. Okay, so the angular radius is, let's see. Well, let's just say we want to get to the first dark fringe. So the first minimum on there. So that's going to be the outer edge of that bright maximum. And then you have that dark fringe. So to the first dark fringe, so theta sub 1, because it's the first dark fringe, is about equal to 1.22 lambda over d, where capital D in this case is the diameter of the circular aperture. I'm not saying slit anymore because aperture is more general than the slit. Okay. And this is in radians. Lambda is the wavelength of light used. D is the diameter of the aperture. Notice again, as with the single slit diffraction, that it's proportional, the size of this pattern is proportional to the wavelength. Longer wavelength, wider diffraction pattern. But, and just as before, the wider the aperture, the narrower the diffraction pattern. Okay, I'm not going to even bother solving for the Y positions of these fringes on the screen because it's exactly the same math as when we did with the single slit diffraction. You're just taking the tangent of that angle, theta. You've got a distance to the screen, L, and you've got a Y position there for that. Tangent of theta is Y over L. We're using small angles, so tangent of theta is about equal to theta, so theta will be Y over L solved for Y. Just put that in there. Okay. Now, this 1.22 lambda over D comes up in several other places. Why is a circular aperture useful at all, besides it's one of many kinds of shapes? Because telescopes have circular apertures. Microscopes have circular apertures, and for that matter, the human eye has a circular aperture. That's your pupil. The hole left open by the iris, which changes the size of the pupil. So your eye has a pupil of diameter D, which is small, 2 to 4 millimeters in bright daylight for the smallest, and it varies from person to person. And of course, it's wider in dim light because your eye is trying to let in more light so you can see better in the dark. So, the diffraction pattern of light through a telescope, a microscope, or your eye looks like this. To the extent that you don't have other blurring effects at work. If your eye's lens is not really in good shape, literally, then it will affect that. But ideally, under perfect conditions, this is the appearance of any pinpoint of light that you're looking at. A pinpoint of light, what we call a point source, if you're standing far away from it so that it looks infinitely small, just a dot, that light will be a plane wave as it comes into your eye or through a telescope. So a distant star viewed through a telescope is essentially a point source, and it has produced a plane wave because those spherical waves, by the time they've gotten all the way out to the tiny section that's caught by the telescope, they're all parallel to each other. Rather than spreading outward, they're running in parallel lines. So, you get this pattern. Now, that means that, let's see here. Okay, so the picture of a star, when you take a photograph of a star through a telescope, stars look round, right? The reason that stars look round through a telescope is not because stars are round, although they are. It's because the diffraction pattern is round. And primarily because the bright central maximum is so much brighter than these bright fringes surrounding it. Those are actually much fainter than the central maximum. Most of what you see is just that central maximum, which is round. The stars themselves, if you didn't have diffraction of light, if it were just straight rays and no rippling out, they would be smaller than a pixel. You have never seen the shape of a star other than the sun. And one other example, the star Betelgeuse, which is the left shoulder, as we look at it, in Orion. It's a bright red star in the constellation of Orion. Betelgeuse is so big and relatively close to our solar system that the Hubble Space Telescope was able to, what we'll say, resolve the shape of it. That means that its shape is wider than the airy disk, or at least in the bright central maximum. And so we can make out that shape. All other stars are smaller than their airy disk through a telescope, even the most powerful ones. Therefore, all you see is that. Now, in fact, you do see a little bit else. Through the Hubble Space Telescope, stars look like this. you get what we call the spider pattern, or these are called diffraction spikes. Here's the airy disk, and you can sometimes make out, if it's a bright star, you can make out one or two rings there. You've got the airy disk, and then you've got these streaks coming out. Now, these are caused by the diffraction of light around struts. Just they're metal struts that are holding one of the mirrors in place, and they block a bit of the light coming through. Not much to worry about. But remember, the diffraction pattern of light will make a streak perpendicular to any edge the light passes over. So if the strut is horizontal, it makes a vertical streak, and therefore you get an interference between those, which make a ripple. Now, so a strut that's on this angle will make a streak, a diffraction pattern, a diffraction spike that's at this angle. And a strut at this angle makes one at this angle. They're 90 degrees apart from each other. And then the circular opening and circular mirror of the telescope produce the airy disk, and then its ripples around that. Now, when I talk about resolving some shape, what does that mean? It means that the shape of an object, the details that we're looking for, are bigger than the central maximum of the airy disk. If it's smaller than that, we cannot see the shape. We might see that there's a little distortion to the airy disk, but we can't tell what it is. Now, there is a way of telling when you'll be able to resolve a shape. Let's say that, for simplicity's sake, we're looking at two stars, because those are going to be point sources. Two stars that are close together. How close together can they be and still tell that they are two separate stars? What we're going to say is this criterion is that the first minimum of one star's airy disk, overlaps the central maximum of the other stars. If they're farther apart than that, we'll say that they are resolved, separately resolved. If they're closer together than that, then they are unresolved. They just blur together into one. So, unresolved would be, let's see if that's on the screen. Yes. There's one. Now let me make its fringes. I'm just going to do the central max and the first fringe, first bright fringe. Now, if the other star is, say, this close in, now I draw its pattern. Like that. Now you get interference. So the bright there and the dark here cancel, and you wind up with just sort of a slightly broader area. It looks almost like a face there. So this is unresolved. If it's marginally resolved, or meaning just barely resolved, then there's one. Let me draw its first bright fringe. Okay, so there's the first dark fringe, and I'll line that up with the central maximum, the center of the other one. There. And the interference between those two gets me this. Now, this isn't very well resolved. But it's just enough that we can kind of tell. You can see the shape has a little pinch point there. If I look at the cross section of this here, let me use red and blue. We'll hope that the red shows up well enough. So that one I'll draw in red. Okay. Now, the first minimum of this one is where the maximum is of that one. Let's see. So when you add those two together, the sum has a noticeable little dip in the middle, where it's just a little bit fainter than those sides there. Marginally resolved. Now that means, because we know the angle between the central maximum and the first dark minimum, the first minimum, that means the distance between these, the angular distance between them, is 1.22 lambda over d. So, and if they're well resolved, then they're farther apart than that. Like that. So theta is greater than 1.22 lambda over d. And over here, for unresolved, it's less than 1.22 lambda over d. As a rule of thumb, 1.22, you can, if you're just doing it in your head, mentally you can round it off to 1, and you're going to be off by 20%, 22%. But then the wavelength divided by the diameter is going to give you a rough estimate of the angle in radians that you need to have them separated by. So what does that mean in practice then? Oh, and let me make a note that this is called the Rayleigh criterion. Okay. Now, as before, when it's marginally resolved or better, that means that the angle that they're going to be separated by is proportional to the wavelength. So if you want a sharper picture, you want to decrease the size of the area disk and sharpen the picture. That means you need a shorter wavelength, so don't use red light, use blue light or violet. Use a larger diameter lens or telescope or whatever. And yeah, those are the things there. So let me give you two examples. First, what is the smallest detail the human eye could see if your lens is otherwise perfect and under good sky conditions, visibility conditions? And secondly, how small an object can a spy satellite really tell from being up in Earth orbit? Okay, so what can the human eye see, at least in principle? The pupil size under bright light ranges from about 2 to 4 millimeters. So let's put it on the wide side and say 4 millimeters, which is 4 times 10 to the minus 3 meters. Now notice, this fraction here, the ratio, is of length over length. So I want my units to be the same, or put them into the same units, so that those cancel out and give me a dimensionless ratio, which is in radians. All right, the eye is most sensitive to light with a wavelength of about 550 nanometers, which is in the yellow and green side. So let's use 550 nanometers, which is 550 times 10 to the minus 9 meters. All right, and that's all we need. So the minimum angular size is something that we can see features on, distinguish two spots on it, is going to be 1.22 lambda over d radians. So that means 1.22 times 4 times 10 to the minus 3rd meters divided by 550 times 10 to the minus 9th meters. I'm not even going to try writing all of that out. So that's going to get me 1.68 times 10 to the minus 4 radians. Hallelujah, what a wonderful result. What does that actually mean? I mean, it's in radians. That's not an everyday kind of a unit. Let's put it into degrees. So, I can multiply anything by 1 without changing it. But if I cleverly disguise 1 with different units, numerator and denominator, if I say that 1 radian, let's say 2 pi radians is equal to 360 degrees. The radians will cancel, and all I've done is multiply by 1. You can take that through, and you've got 9.61 times 10 to the minus 3 degrees. So it's 9 thousandths of a degree, almost 1/100th of a degree. Let's see about doing something else then. Let's put it into arc minutes or arc seconds. So 1 degree is composed of 60 arc minutes, minutes of arc, to distinguish them from minutes of time. And 1 minute of arc is composed of 60 arc seconds. Let's multiply through by that. So a degree is equal to 60 minutes, and a minute is equal to 60 arc seconds. Degrees cancel, minutes cancel, and I've got this number of degrees times 60 seconds, 3,600, and I get 34.6 arc seconds. Which is pretty small. Well, that makes some sense though. Our eyes are pretty good. I mean, a degree is about, depending on the person, roughly the width of your thumb held at arm's length. It's about a degree, maybe, I think for me this is wider than 1 degree. My fist here is close to 10 degrees. And thumb is, it's going to be about 1/4 or 1/5 of the fist width. So maybe that's like 2 degrees. Pinky is going to be closer to 1 degree, perhaps. That's a very tiny amount. But then again, I can see details on my thumb held at this length, so that shouldn't be too surprising. Now, in reality, in practice, I should say, this is still reality. In practice, you may not be able to see things that are that small because your eyesight might not be very good. Or for that matter, you might have the air in between you and what you're looking at could be swirling around because of heat going through. Other things can make this diffraction limit make you not be able to see things that are really this small. This, though, is the smallest thing that you could see ever under these conditions. Yellow to green light and your pupil fairly constricted. With your pupil more dilated, you would be able to see things sharper, except that your lens will have what's called spherical aberration as the pupil opens up, and it would actually blur things out. So, you gain something, you lose something. Now, what about spy satellites? You hear reports of spy satellites able to read license plates, able to read headlines on newspapers of people sitting outside. What can they really do? Now, the thing is, they don't really tell us much about what spy satellites can do because you don't want the enemy to know. So we can make some guesses, though. One of those is that it's pretty well accepted that the Hubble Space Telescope, I'll use the abbreviation HST for that. The Hubble Space Telescope is about the size, and we think a similar optical design to the KH-11 class of spy satellites that were launched back in the, I think they may have started in the 1970s, maybe 1980s. The Hubble's launched in 80. Hubble was supposed to be launched in 86, except the Space Shuttle Challenger blew up and delayed it until 1990. So maybe the KH-11 series, the Keyhole, their nickname, KH Keyhole, the Keyhole 11 series are roughly that same time period. Now the Hubble has a main mirror with a diameter of 2.4 meters. Now, let's say about the wavelength of light. We want to use a short wavelength to get the sharpest possible image. Violet light, the human eye can only see down to the shortest wavelength is about 380 nanometers. Let's round it off to about 400. You've also got the absorption of the atmosphere. It's pretty strong when you go into the ultraviolet. So let's go to 400 nanometers. So that is 400 times 10 to the minus 9 meters. Okay, so let's get an angular size. The minimum angle that can be resolved for the Hubble or for this kind of a spy satellite, say KH-11 class, is 1.22 lambda over d, which is I see here I actually worked through to the physical size on the ground first, but I want to get you an idea of what that angular size is. So I'm going to have to get out my calculator. Meanwhile, you can work through it yourself. Okay, so that is 400 times 10 to the minus 9th meters over 2.4 meters, which gets us, let's see, 1.22 times 400 exponent to the 9th divided by 2.4. Boy, that's a small number. So I've got 2.03 times 10 to the 1, 2, 3, 4, 5, 6, 7 minus 7th radians. Okay. Well, I've done that roughly correctly. To put that into arc seconds, I multiply by, let's see, degrees, so times 360 degrees per 2 pi radians, and then times 60 arc minutes per degree, times 60 arc seconds per minute, and that's going to cancel radians, degrees, and minutes, leaving seconds. So, times 360 divided by, parentheses, 2 times, where's pi? Pi. Equals, all right, then times 60 times 60, and I get 0.042 arc seconds. And that, I happen to know, is about right. So, a tenth of an arc second is the size of some of the wider pixels on the early cameras on the Hubble, and then the finer pixels that they used in the later cameras are about this size, or even half again that size. This is rough, but that I think is pretty close. Okay, now, what about the size of an object on the ground? All right, so there's our spy satellite facing downward. Now the Hubble, of course, faces upward, but we do turn it upside down sometimes because we're trying to get some bright light to calibrate the instruments. There's our minimum angle, greatly exaggerated. And here is the width. I'm going to use lowercase l for length, say. of something on the ground, and how high up are we? How high is the orbit? That's going to be h. Now, to cut that angle there, now really, I'm going to be looking at something that's straight on like that, but I'm going to avoid a little bit of the half that angle and half that length. For a small angle, I can get away with doing this. That's L, that's the height, and that's my angle there. If the angle is small, that'll give me the same result as a triangle where I'm an isosceles triangle. Okay, so tangent of the angle is equal to opposite over adjacent, length of the object on the ground divided by the height of the satellite. And I know that tangent of theta for a small angle, and believe me, this is a very small angle, is about equal to theta. So, if I want to solve for what length of object, I multiply the angle. It's got to be in radians here. Otherwise, I'd have the unit degrees or arc seconds running around. Radians are a dimensionless unit. So if I've got length here, I've got length here, dimensions. So if I put the numbers in, let's see here. 2.03 times 10 to the minus 7 radians times the height. What height? The Hubble orbits at an altitude of about 300 nautical miles. N period MI for miles. We used to just put NM for nautical miles, and then the French started using NM for nanometers. So, all right, 300 nautical miles. Let's put it into meters, because that's what I've got for the other units. That gets me something. Here we go. 5.6 times 10 to the 5th meters. So if I put that in, multiply by the angle in radians, I get a length which is 0.11 meters. That's 11 centimeters, or about 4.3 inches. About the width of the palm of your hand. Now, at that resolution, it's not going to be reading a license plate. I mean, the width of your letters on the license plate is something like that size, and you've got to be able to resolve the features of the letter to tell one letter from another. You'd be able to see the license plate, you'd certainly be able to see what kind of car. But there are techniques for improving your resolution. And it turns out you can, deconvolve the diffraction pattern, the area disk, and the image that you actually get, the blurry image that it creates. If you deconvolve the two, you unblur it, you can, to some extent, recover the idealized shape of the image that you're seeing. What happens is that if you have a picture, all right, so you take a picture, you shine light through it, you projected this image. Let's say that that's your idealized image. When you actually take a photograph of that with your telescope, that idealized perfect image, which never really exists, going through the telescope, has that area disk, it has that diffraction pattern. For every infinitely small point of light in that image, that point of light is spread out by the area disk, or by whatever the diffraction pattern is for your scope. Therefore, the whole thing is blurred by that. Now, in mathematics, we say that the image, which is a function, it's a two-dimensional function. It tells you how bright the light is at a point in space in x and y. It's a 2D function. The area function is a function, a two-dimensional function. We're taking the image function as the input to the Airy function, and what we get out is the real picture that we see, the blurry picture. In mathematical terms, we say we're convolving the idealized image with the diffraction pattern to get the real image, which is blurry. Well, we can mathematically deconvolve. We can reverse the process. More or less well, and usually less well, because we always have an imperfect knowledge of what the diffraction pattern through the telescope really looks like. We can make mathematical models of it, but we're always going to have imperfections of the knowledge, which means that when we deconvolve it, we wind up creating shapes that aren't even really there. But sometimes we can live with that. So anyway, deconvolution can be used to improve this. We can get beyond the diffraction limit to some extent. Okay. Let's see. That gets us through diffraction through a circular aperture. Now let's take a look at interferometry. Okay, an interferometer is an instrument that breaks a light wave or a sound wave or any other wave into two paths, and then it lets them combine again to interfere with each other. Then the pattern you get out, the interference pattern, whether you get constructive or destructive interference will only depend on the different path length taken by the two branches. An example given in the book is for sound. Let's say I've got an audio speaker here. It shows up sort of. Well, I'm going to draw the squiggly sound wave. Now let's say it goes through a tube, and then I split the tube into two paths. Okay, so that half the sound goes this way, and the other half goes this way. Now, you can see when they recombine, they could be in phase or out of phase or somewhere in between. So, if they're exactly in phase, you would hear a much louder sound. Well, you would hear the full strength of the sound. If they are out of phase, exactly out of phase, you get perfect destructive interference, you'd hear no sound. And if they're in between, it'd be in between. Now, we can change that by lengthening this section of tube here. So the extra path length, which is going to be, let's see, that, minus whatever that is there, that's the path difference, will tell us how much in or out of phase they are. Now, by listening here, if you hear no sound, then you know you cancel them out. And you know the path difference is equal to an odd number of half wavelengths. Remember, if it's an even number of half wavelengths, that's the same as an even number of wavelengths, which is, or a whole number of wavelengths, which is constructive interference. So if you get them nulled out, canceled out, now you know that at that, whatever the wavelength is, you don't know it yet, but you know that they're off by half a wave. Now, pull this tube out a bit more to lengthen the path. The sound will get louder again, and then it will get softer again and go to the next cancellation. Now, you measure the distance that you've moved it there, and you know that that is equal to half a wavelength. One whole wavelength to go from cancellation to the next cancellation. And that allows you very easily to measure, because you can look on a micrometer scale here, how far you've moved it. You can measure the wavelength of the sound very precisely. With light, we can do the same thing. With light, an interesting kind of interferometer is the Michelson interferometer. Now, we take it could be a laser beam or any other source of a single wavelength of light. We don't want a broad spectrum of light, because then you have different wavelengths to deal with. So we've got a source here. I'll just draw the symbol of a star, but it could be a laser or something like that. All right, so the light is shined onto what's called a beam splitter. And now that I've written Michelson interferometer, I've got to erase it, because I don't have the room here. We shine the light onto a beam splitter. Now this is transparent glass. Glass, though, reflects a bit. And this is designed to reflect half the light and to transmit the other half of the light. So it splits the light beam into two, roughly equal strength pieces. Now I'm going to have a mirror up here. It's in the picture. Yeah. And I'll have another mirror over here. So, light beam coming in, hits the beam splitter. Half of it goes on through. Hits that mirror, reflects off, hits the beam splitter. Now part of that goes through as well, but we're only interested in the part that's then reflected down here. Now there's going to be a person looking down there. That's the universal physics symbol for an eyeball. It's the edge of an eye with the eyelashes here. So, now, what about the other beam? So it goes up, the part that's reflected, does that, hits mirror number one, comes down, of course, half of it's reflected again, but we only care about the part that's transmitted, and comes on there. All right, so a single source, so that the waves that come out are in phase with each other, all right? And then if they're in phase or out of phase, that depends on the difference between the distance L1 to the first mirror versus L2 from the beam splitter to the second mirror. And we measure from the beam splitter because that's the last time that we know for sure they're in phase with each other. Okay, now the length that it travels up here and back is 2L1, is this path length here. And the length that it travels here and back here is 2L2. And then when they recombine, well, they're either, if they're in phase at this point, they'll be in phase when we get down here because they're traveling the same path there. Now, the path difference delta R is the difference between 2L2 and 2L1. Okay, well that just means 2 times L2 minus L1. Now let's say I'm looking for constructive interference. That means a whole integer number of wavelengths. So that means the path difference must be an integer times lambda. So that's for constructive interference. I've run out of room, I'll just put constructive. All right. let's solve for the path difference that hits that chicken. So that's going to mean, oh, I divide by 2, sure. 1/2 m lambda equals L2 minus L1. Let me erase the phrase mirror 2. All right. So constructive interference requires that the difference between those two arms, these are called the interferometer arms, is 1/2 m lambda, whatever m happens to be, 0, 1, 2, and so on. Now, how this is used, though, because you don't inherently know, if you don't know the wavelength, then you don't know which m you're looking at for constructive interference. So what this is used for is in changing the wave, the path difference. We can use a little screw to slowly move that arm out, that mirror out, lengthening the difference between those two. So let's say that we hold mirror 1 fixed in place and we slide mirror 2 out, meaning we increase L2, that length of that arm. So holding L1 fixed, change L2. All right. As that changes, we're going to go and see how much we change to get to the next constructive interference. So I make everything is going to be the new L2 minus the conditions for the old L2. Will be 1/2 now. I'm changing. So delta m times lambda, I'll put delta m in parentheses because lambda is not changing, equals the change in L2 minus, well, the change in L1 is 0. It's not changing. There we go. Now, what I'm interested in is counting how many bright constructive interference cases I see. As I lengthen this arm by an amount delta L2, how many times do I count another bright fringe, another one? That's delta m, the number that I count as I change this. So solving for delta m, that equals 2 delta L2 over lambda. The number of bright fringes you see, the number that you count, you go from bright to dim to bright to dim as you change that position of mirror 2, as you move through distance delta L2. Okay, what is this good for then? Wonderful toy. If you know your interferometer arm lengths very accurately, but you don't know the wavelength of light very accurately, you can use the well-measured laboratory lengths to measure the wavelength of light. So that's the first thing that this is used for. Now, because the wavelength of light also depends on speed of light. This was the first big application of this was by Michelson and Morley in the 1880s. And they were measuring the speed of light and when the Earth moved in different directions. There was the idea that light was a vibration of what's called the ether, some kind of a material that we don't think exists, at least not in that form, that light vibrates within to carry it. Because all vibrations, all waves are thought to be vibrations, mechanical vibrations of a thing. Therefore, if the ether is a substance, if it moves, or if the Earth is moving through it, then the speed of light, and therefore the wavelength of light, would be different at different times of the year, as the Earth moves this way to the ether versus that way to the ether. Well, anyway, and I'm rounding off the explanation a bit too much, but so they did experiments back in the 1880s that showed that the speed of light was the same no matter which way the Earth was moving. And that lack of a result, they found no difference as they made these measurements from one angle direction to another to different times of year even. No difference. And that negative result is often considered the most important negative result in all of physics. By not finding a difference to this, this eventually led to the disproving the existence of the ether. Although not everybody was convinced right that year because, well, maybe there's an ether current, an ether drag around the Earth as we go, and that could, anyway, eventually people caught on to it. But this was the first real crack. The second thing is, if you know the wavelength of light by other means very well, then you can use measurements of the wavelength of light and counting the number of fringes you go through to measure the change in position of this mirror. Well, aren't you moving the mirror yourself? Don't you know that? Not necessarily. Because one of the most fantastic uses of this is in the hoped-for detection of gravitational waves, which we have not done yet. But we have built, by we I mean not me actually, but other people. My wife works with this. They have built detectors to look for the gravitational waves, the ripples in the fabric of space-time itself, by the acceleration of massive objects like black holes orbiting around each other would make a ripple in space itself. It would stretch and compress space as this rippled out. Now when that happens, things that are hanging freely, like a pendulum, would start to swing back and forth. Space pushed it a little one way, then pushed it back another, and your momentum would make this thing swing back and forth with a certain speed, certain vibrational frequency. So what happens if you take an interferometer like this, and you hang this mirror by a little fine quartz fiber? In fact, originally I think they were using something like fishing line. They've upgraded it now to quartz fiber, which is very strong and has no problems. Now, if you let it swing back and forth freely, you've got to dampen it so it doesn't swing back and forth because somebody's stomping on the ground. If a gravitational wave comes by and sets it swinging, even the amount that it changes is supposed to be less than the width of a proton. Think about that. That is 10 to the minus 15th meters. That's all that would move. Something on that order. Maybe 10 to the minus 10, but I think it's 10 to the minus 15. How, let's see, 10 to the minus 10 is about the size of an atom, but this is less than that. So how could you ever detect that amount? Well, it turns out that with a Michelson interferometer, very high precision, they can measure that kind of a small change. There are other techniques they've got to apply to it, but they can measure that. And so far, they've also not found anything. Does that mean there are no gravitational waves? No, because the sensitivity that they've got is not yet great enough to detect the vibrational frequencies that they expect from, say, the orbiting black holes and things like that. But this year, this being 2015, they are opening back up. They have upgraded the, it's called LIGO, Laser Interferometer, this is Gravitational Wave Observatory, in Livingston, Louisiana. They've got another one in Hanford, Washington, in eastern Washington State. And the Europeans have now gotten on and built one in Italy and another one in Germany, and there may be some others that people are starting up. So the improved LIGO, which will be even more sensitive, many times more sensitive, should be coming online this year, and we expect it will be sensitive enough to get down to what gravitational waves are predicted to be emitted by spiraling black holes, which is what my wife works with, simulating the gravitational waves. So we're very excited, and this equation, that's it, right there. It's easy enough to understand from an undergraduate standpoint here. All right, and this, that is really all I'm going to do with on interferometry. A hologram is a wonderful topic. The book discusses it, but unfortunately, while I have a couple of wonderful holograms, I can't show them in this kind of a room with that kind of a camera. So we'll just have to wait until the lab day when I can bring you all in and we can look at a nice dark room at holograms. But that's another very good application of interferometry.